first of all, in the autoencoder starter.py file, there is a missing column for this function, the plot kernel function. So please go ahead and add that. And then this function shows the result for like showing the image from the training data set or reconstructed image or even generated unseen samples. So you can use that for print out the image. And also this plot kernel function, I'm going to explain it. Okay, so this is our encoder. Okay, this is our encoder latent variable and then decoder. In fact, it should be something like this, because we go from lower representation to higher representation, and also from higher representation to a lower representation. Okay, and this is our decoder. And for example, image 1 goes in and image 1 hat comes out from the network. And so here, for example, in the MNIST dataset, we have 748 dimensions, and the reason is our images are 28 by 28, and we do a flatten on this image. So, for example, if this grid shows the pixels of an image, so this is, for example, 0, and this is 27, and this is 28, and so forth. And we grab this row and put it here. So 27 is this one, and then 28, and so forth. So this is the flattening thing. So we flatten that, and then we'll have 748 dimensions. And then we use a linear function, a linear layer like 48 as the input. And for example, 30 dimensions as our output. And this is our linear function, right? And from the torch. So now, so this linear layer is like, from 748 dimensions, the image, to, for example, 30 dimensions, and for a specific dimension, for example, for this dimension number 0, or the first dimension, it has a W that multiplies to each of these dimensions, right? To each of these 748 dimensions. This is just for this. And also we have the same number of weights for the dimension number 1, 2, and so forth. So each of this set of weights that goes to a specific dimension is called kernel. So kernel is this, and if you visualize that, it is like template. For example, for the 0, it should be something. So this is again, we have 748 weights, right? So let's visualize it like what we could understand. So again, this is kernel number 0, and we have 28 by 28 image, right? If we do the inverse flatten on this weights, we can get an image. So, for example, assume that this image is to recognize or represent a specific number, like 1. So it should be something like So if we assume this is 1, so this area should be 1, this area, this area, this area, this area, and other pixel should be, I show 0 with black color. So this should be 0, 0, 0, 0, 0, right? So this is like a template. So you need, if you go ahead and plot the kernel, you'll see interesting things. And also this was for the denoising autoencoder. For the denoising autoencoder, we, in our network, we, before feeding the image into our model, we add noise, a Gaussian noise, and we feed that to the network. So it goes to the network, and then we generate the latent representation, and then the decoder reconstruct the I hat, and we calculate the loss between the output and the original input, not the noisy one. So this is the DAE model, which is not required to be implemented in this assignment, but just wanted to let you know. So there is one problem. First, you need to add this colon here to solve the error problem. And also, let's talk about the VAE model. VAE, or variational autoencoder. So in vanilla autoencoder, we have an encoder, a latent representation, and a decoder. So in best case scenario, we want to, if we show this latent representation space with 2D, in 2D. So for example, for the MNIST dataset, in ideal case, we will get, for example, ones here. So they should be close to each other, right? Twos and number 3 samples here, and so forth. So this is, for example, 1, 2, 3, 4. However, I guess you already know that it's not the case. So you see a like not organized latent representation. And as you go to the next step of your assignment, like from A to B and B to C and so forth, you'll see that this latent representation is changing, and there is a reason for that. Now, about the VAE. For the vanilla autoencoder, so we have for 748 in our example, and here, for example, 30 dimensions. And this is the 2D representation of this 30 dimensions. And again, we feed 30 dimensions to the decoder, and it reconstructs for 748. We do the inverse flatten function, and then we get the 28 by 28 input image, which is reconstruct, and the original input image. Okay, here we might have, for example, an activation function. I show it like this, and also here in our decoder we might have activation functions and also linear layers and so forth. But the difference between vanilla autoencoder and variational autoencoder is that after getting this 30 dimension, we feed that to 2 layers. This is what we wanted you to research about. So I give you a clue. So we have in variational autoencoder, we assume that our latent representation space is like a Gaussian distribution, right? So this is a 2D Gaussian distribution. So this is our prior, right? It's called prior. So our prior is that our latent representation is a Gaussian distribution, and after training this network, it brings many features to our latent representation. Anyway, so for this, assume that we get this 30 dimensions representation from the encoder, then we feed that to a linear a linear layer. This is a linear layer for the mean, and another linear layer for the standard deviation. And then we get two 3D variable. Okay. Implement this function for the DAE. This is about the adding noise that I explained, and also the plot kernel thing that we don't want it for the current assignment. And this is for the VAE model. We call it the reparametrization function, and it gets the mu and log var. Mu is this mean, and the log var is this standard deviation. So you need to actually add two layers, this layer and this layer, two linear layers to predict the mean and standard deviation from the encoder output. Yeah, it gets the mu and log var, and then during the training we add noise to the using a formula. You need to find it, and at the inference time, or when we want to create a new sample after training the network, we want to create a new sample or visualize the latent representation and so forth, we don't use this reparametrization function, and we just output the mean. So this is compared to DAE one, which was here. Okay, this is the DAE network. So in vanilla autoencoder, we have an encoder latent and decoder. In DAE, we added noise at the beginning of the network. And in VAE, we add noise here. So this is, for example, let's say our output is our encoder output is located, for example, here. And using VAE, it considers a Gaussian distribution around this point with a standard deviation, and take a sample from this area. So assume that we have a Gaussian distribution and the mu is this point, and we want to take a sample from this. So instead of feeding this point to the exact point to the decoder, we take a sample. For example, it might be, for example, this one. So we feed that to the decoder. It goes to the decoder. And so this is the difference between vanilla, DAE, and VAE autoencoder. So you need to, in the reparametrization function, as a function that take a sample from this distribution. And also, in order to create this mean and standard deviation, you need two linear layers. So now let's go to the question B, C, and D. Okay, a variational autoencoder trained by adding KL divergence term to the loss function and a VAE. Okay, so for the adding KL divergence term to the function, you need to put it here in the loss function in the starter code. So you have a loss function. Already the training process is implemented, so you don't need to think too much about it. But here, this is a mean square loss, which is already working, and you need to add the KLD term, like for example, KLD equals to something, and then return loss equals to BCE plus KLD. So mean square plus KLD. So one line of code, so you put the KLD term here. After copying this autoencoder starter pi and rename it to something autoencoder starter pi and name it VAE starter. So so this is about the starter pi.file and a VAE encoder and input This is distribution over the latent space. Okay, implement a vanilla autoencoder similar to the part A with bottleneck size of 30 dimensions. So let's go to part A and see what we had here. Implement the architecture of the encoder and decoder and print out the also use the scatter consists of no hidden layer and one fully connected dense output layer known as linear. The bottleneck feature represents Z should be two-dimensional. The decoder's output should be transformed by a sigmoid function. Okay. So this is the architecture of the part A, encoder, decoder. I'm writing through the code guys here. Linear, oops, linear 2 to 748, and then a sigmoid function. So the input image 28 by 28 goes to flatten, and we get 748, and then it maps to that to 2D dimensions, and then we use that 2D dimensions and map it back to 748 dimensions, and then feed that to the sigmoid function, and we get the output image. Flatten 748 to 28, 28. Image hat. This is the reconstruct. And so this is the original input. So this is for the part A. In part D, it says starting from the implement a vanilla autoencoder similar to the part A with bottleneck size of 30. So we change it to 30 dimensions. Pick another, okay, 30, and this is again 30 dimensions, and everything is the same. And then afterward, change the autoencoder to a variational autoencoder by adding a KLD term to the loss function and train the model with different weight on the KLD term from this subset. Okay. So for this part, first of all, you need to change it a bit. First, you need to implement the two mean or mu and std layers. So this goes here to this point, 30 dimensions, and we get two 30 dimensions, and then we feed them to reparameterization function, and take a sample, and then sample has 30 dimensions, and then it goes to the decoder here. So you need to implement these two layers, these two layers, and also the reparameterization function, and then take a sample and feed that to the decoder. And also, I guess you need to change the activation function or something Turn to the loss function and train the model with different. Oh, by the way, this here you need to put a weight here, like W. You might use an argument, or you can just change it by hand and then report the plot from this models with weight 0.5, 1, and 4, and also explain what's going on there and what's the reason of difference between different plots from different KD term rates. Okay, I'm gonna stop sharing and recording.